So, hi everyone. This is the seventh episode of the Fright Circuit, and today we have with us a very special guest. Uh, of course, we have Shikhar as well, who will be in this discussion. But I want to talk about first our guest, who's Mr. Aditya Vijaykumar. He's a Fulbright Nehru Scholar at the esteemed University of Chicago and a PhD candidate in physics at the International Center for Theoretical Sciences in Bangalore, Karnataka. He's completed his undergraduate degree in physics and mechanical engineering from the Birla Institute of Technology and Science, and he also has an extensive background in astronomy and astrophysics. He's currently working on various physics and astrophysics aspects of gravitational waves, combining both theory and computation, as well as understanding of experimental data from gravitational wave detectors. In addition to purely academic research, he's also a talented blogger, reader of Indian fiction, and a lover of new cinema and creative writing. When not working on research, he directs and acts in stage theater productions with the theater outfit StageCraft and runs a podcast called Cut to Scene. You can check out all of his work via his Google Scholar or GitHub pages that have been linked in the description below. Thank you so much for joining us, Mr. Vijaykumar.
Thank you, Adarsh, and thank you, Shikhar, and just call me Aditya.
Sure.
Yeah.
So I think before we begin, I just want to sort of backtrack, like before we delve into gravitational waves and what your research as well is, I want to just delve into a bit of history of gravitational waves as a whole, so that lays a good like understanding and background for everyone listening. So my basic understanding is that gravitational waves are ripples in space-time that are caused by massive objects moving with sort of extreme accelerations, and I think it probably starts off with all the way back in 1687 when the law of gravity was first proposed, in the sense that the difference was that at that point we had a loose understanding where we believed that it was something that was acting at a distance and it was almost instantaneous. And then sort of through the 18th century, you had the dynamical theory of electromagnetic fields introduced by James Maxwell, and then it sort of there was attempts to unify gravity with those sort of with other fields of magnetism and electromagnetism as well. But it all culminated in Einstein's theory of special relativity, and that firmly established that gravity traveled at a fixed velocity, and that it was a product of space and time behaving, as you would see that famous trampoline envisionment. But I want to move away from the history and talk about while Einstein's theory of relativity predicted these gravitational waves. It was confirmed, I think, 14 September 2015 was when we caught them at the Laser Interferometer Gravitational Wave Observatory, or LIGO. So I think the perfect way to start off, everyone, would be that while this history lesson is a bit boring, I would want to ask you where you were, or where you sort of were as a student and as a physicist when we sort of discovered gravitational waves, and the kind of impact that it had on you, not only as a person, but sort of someone who is looking to delve into astronomy as a physicist.
Yeah, that's actually a very nice question. And I do have a story associated. Well, not a very interesting story, but a story associated with it. So 2015 was when I was just entering third year of college. So August 2015 is when I started third year of my college. And just before the third year, I interned at this place called the National Center for Radio Astrophysics, which is in Pune. They run one of the largest telescopes in the world, called the Giant Meter Wave Radio Telescope. And I was working on those kind of problems, and I was also, sort of revising all my general relativity basics and so on. And that is actually when I first came across gravitational waves. I had no idea what they were before that. Remember that the first detection was not made at all. So it was very difficult to know what gravitational waves really were. And it's very interesting how I got to know about gravitational waves is because one of my seniors in college, Vijay Verma, he was basically he interned under my current advisor, and he had gotten admission into Caltech, and so that's how I even came to know that there's a field called gravitational waves, just because there was some threads which led to gravitational waves. And yeah, I mean, I guess I don't remember what exactly I was doing on when the first detection was announced. It was always, I mean, I don't, you guys were probably much younger at that time, but then, so the detection was made on 14 September, but it was only announced somewhere in February 2016. So it took like a few months for people to understand that, there is some sort of signal in the data. And then it was only released to the public in the February of 2016. In this time, there was, I mean, personally, I had read more and more about gravitational waves, but there was also like rumors going around. So I was active on Twitter, and there were some rumors here and there going around that, LIGO has really detected gravitational waves, and basically also, they will be announcing it soon and so on, right? And so yeah, that's that craze. I mean, that was probably the first time as an adult where I felt this craze of some scientific revolution waiting to happen. Because before that, I think the big breakthrough in physics was the detection of the Higgs boson, and I was too young at that point. So yeah, it was like one of the first things. And then I remember also trying to apply to all these internships in gravitational wave astronomy, and I got into none. So I ended up doing other forms of astronomy in my internship the next year. Uh, but yeah, I mean, this is the small story. And one thing I should say is that I was like right since the first detection, and even before it, I was very into gravitational wave astronomy because before like I mentioned that I was interning at this place in May 2015, and that in that place I worked on radio astronomy, and I realized while trying to read introductory gravitational wave astronomy stuff that the methods used in radio astronomy are pretty similar to those in gravitational wave astronomy. So I always thought that I could extend my skill set by also getting to know about gravitational waves, and here I am.
Well, no, so that's, I think, no, I expected it to be something that since you are so involved in gravitational astronomy, I thought it was something that you were dead set on like doing from the beginning. So it was sort of
Not at
more,
all. Not at
yeah.
all.
So I think that's
Yeah.
interesting. So, I mean, hypothetically, if that discovery was not made, do you think you would not be in the current field? And you are.
Yeah, I mean, it's difficult to talk about hypothetical stuff. Um, I would, I think a lot of us would not have been in this field. The field would, I mean, personally, yes, I think I would not have been in the field, but there's also like a whole trickle down sort of effect. Like, for instance, if the first detection had not happened, the field would not have been so big. There would not have been so much funding for the field and so on. So, I'm not sure that even if I wanted to do gravitational wave astronomy, would I have been able to do gravitational wave astronomy in the sense that would the funding situation and like if people can hire PhD students or not, would that all come together? Yeah.
Yeah, I think that's interesting.
So
But
when it comes,
yeah, Shikhar, do you want to say something? Yeah.
so when it comes to scientific research, do you think
Yeah.
institutions generally help in funding only when there's some big news that creates a ripple effect throughout the world, something that has the common man interested, or do you think they do it for the plain progress of science so that you could create that ripple effect at some point in time?
It's a very tricky question to answer. I mean, yes, of course, like if it was any sane funding organization or something, they would really want to see some results out of the funds that they give. Uh, the sad part, or the not sad part, or the fortunate or unfortunate part is that science generally does not work that way. You cannot. It's very difficult to have guaranteed returns in science. So I know that there are some people, for instance, let's talk about India's context, right? Like the giant meter wave radio telescope, the telescope that I mentioned is one of the
Yeah.
biggest in the world. I mean, it was created at a time where it was not really obvious what the result of it is going to be. Like, I mean, I would think of it as like a government, like India's government, putting their whole might about on a project which was actually revolutionary for its time, at least. Even before that, like especially the field of radio astronomy has been very well developed in India, right from the 1950s and 60s, right? And you would think that in the 1950s and 60s, the country might have had other priorities. We were just coming out of like a freedom struggle, and we had finally gotten independence, and we had all these big problems to solve. But even then, I mean, there were clearly some people within the scientific establishment who thought that such types of research are worth doing. even in the current day, I think it depends. There are some people who put their might behind projects no matter what, but then
Yeah.
of course there are some people who are cautious. So it's always a mix of stuff, and I think it's all the same. I mean, I think it's the same even in the US, for instance. Uh, like, of course, the US would fund something like $1 billion experiment like LIGO with no real guarantees of any returns. But then there are also other cases in which the funding agencies are much more, conservative about
Yeah.
where to give the money. Yeah.
Yeah, for sure, for sure. Yeah.
Yeah, so I think, like, I was going to talk about this later eventually, but since you mentioned his Higgs boson being probably the biggest
Hmm.
discovery before gravitational waves, I
Hmm.
think that's a good jumping point into where we can start off with discussing gravitational waves as well. So I think
Mhm.
what the parallel that I would want to draw is that when Higgs boson was starting to create rumors, as you said, was the case for gravitational
Mhm.
waves. I think the difference is that everyone sort of expected that it would eventually be found because like the theory made sense. People were
Hmm.
trying to, at least it was decades in the works of happening. But in the case of gravitational waves, we weren't sure that
Hmm.
we'd ever be technically capable or not to at least catch gravitational waves.
Mhm.
So do you think that, like, I think that's a good way to jump off into like the engineering capability or like the amount of skill that it took eventually to be able to catch them, because as compared to Higgs boson, it was not something that you could be 100% sure that we'd actually end up finding.
Yeah, I will disagree a bit with you there, in the sense that um, it's true that Einstein, when he first wrote down the equations and sort of did some basic analyses, he figured out that the displacements that it would produce on like everyday objects would be very, very low, and then which turned out to be right. They are very, very low displacements, and he said that you can't detect them at all. But I guess it is. Right from the 1970s and 80s, there was this whole research program which was started by people who eventually went on to win the Nobel Prize for the discovery. This was Rainer Weiss at MIT and Kip Thorne at Caltech, and then other friends and collaborators of themselves, like Ron Drever, who was also in England. So basically, these people started an effort, and a lot of work in Kip Thorne's group went behind showing that you could first of all uh, you know um, have sources that produce gravitational waves, which and you can sort of derive how much energy they would emit in the process and so on. Then there was also some work which went on to showing that, I mean, sure. One statement is saying that there are, if the black holes merge, they will produce so many gravitational waves, or these gravitational waves of so much intensity. But then, how do you form merging black holes? Like the astrophysical aspects of it, that was not known, and there was also a lot of work done in Kip Thorne's group and by others on that aspect. But on the experimental side, Rainer Weiss has essentially solved a lot of the you know in principle engineering problems when he wrote down uh, the uh, the way to create the interferometer, right? So I think from the 1980s onwards, we're pretty confident that our that interferometers would be able to detect gravitational waves. Now the question was mostly, do merging fineries form in nature, for instance? Like, do will black holes ever merge in the history of the universe? Those were the kind of open questions, and I guess those questions were what were answered on September 14, 2015. That yes, you can form massive black holes that merge uh, in like some sufficient amount of time before, let's say, before all of us die, say, right? So yeah, I think that is true. And if you compare it to the Higgs boson, yes, I mean, like with the Higgs boson, it was so that the standard model made this the naturally predicted this boson, which gave all fields its mass. But yeah, I mean, like, that's true, but people didn't know the mass of the Higgs boson. They still don't. I mean, they know the mass of the Higgs boson, but they can't explain it very well even now. So I would think that those problems are on the same footing. Like, it's true that gravitational waves were not as well known as the Higgs boson, but I just think it's just a matter of the fact that it was probably not publicized that much.
Oh, so I think I was not aware of that. I thought it was more to do with actually catching them. So it was more the fact that we weren't sure whether black holes would merge in the first place, rather than being worried about whether we would.
Yeah. Yeah, I mean, I think I think the chronology of events is as follows. Like Einstein wrote down the equations and he said that the displacement is going to be, I don't know, like 10 to the minus 20 meters or whatever, right? And then the challenge then was, how do you measure displacements as small as this? And the way to do that was given by Rainer Weiss in the 1970s. So I think the fact that you can measure such displacements was already proven in the lab. But how would you, I mean, how long will you have to wait before you detect one, was something that was an open question.
Okay, so I think that probably the next ideal line of questioning would be something that I want to understand, in the sense that, you said that they're of really small magnitudes, the waves that have been created, right? Essentially.
Yes.
So
Yeah.
is it like supposing, is it necessary that only black hole mergers do create gravitational waves, or is it like even smaller astronomical uh objects would also be creating gravitational waves?
Yeah, that's a good question. Now, one should remember that to create gravitational waves, you need two things. You need massive objects, so very objects that have a lot of matter, or objects that have a lot of mass coming very close to each other, right? So you need very massive objects very close to each other. The very massive means the mass, like the density should, so not just mass, their density should also be high. Like they should be very compact objects and they should be very close together, meaning their velocities are high. Now, if you remember Kepler's laws from school, it says that what you say, the t square is proportional to r cube, right? So, or the frequency square is proportional to 1 by r cube, which means you need something, and the frequency roughly goes as velocity cube, I think. So basically, you want something which, if you have very low separations, you will also have very high velocities. When you have very high velocities, especially velocities comparable to the speed of light, you are no longer describable by normal Newtonian mechanics, and you need to resort to general relativity and special relativity to calculate how much gravitational waves are emitted, for instance. So yeah, so basically any object that is very massive and can any two objects that are very massive and can come close to each other can produce gravitational waves, right? So now, like for instance, binary black holes can produce gravitational waves. There's a class of stars called neutron stars, which are these ultra dense stars, but unlike black holes, they don't have a horizon. There's no point of no return in them, and they're made up of matter, just a very exotic form of matter. So those can produce gravitational waves, and we have seen gravitational waves coming from a merger of two neutron stars in August 2017, so a few years back, and those are also really cool. Binary neutron star especially very cool because unlike black holes, there's matter inside these neutron stars. So when they collide, they actually give out a lot of energy, which can be converted into light. So it can convert all the energy of the inspiral into energy in light and other forms of radiation. And we can detect gravitational waves from the gravitational wave signal, but we can also detect light from the light that is produced after it merges. So it was a very unique signal in that sense, and actually probably the most followed up astronomical event ever on the planet. So yeah.
So I think what I think makes sense to understand is that, so when you say that gravitational waves are being produced at the same time as light is also being produced, but if we as observers or anyone, if I don't know if it would reach us at the same, it would not be too dignified to reach us, but supposing you were close enough to actually measure it, would the light be more affected while you're measuring, or the gravitational waves? Like, essentially my question is that when gravitational waves are traveling to us, all the way to us, is the reason that they're harder and harder to detect the fact that they're just decreasing in magnitude over the distance they're traveling, or because they're interfering with things in space, or are they not affected by that?
Interesting. Yeah, so this definitely happens to light, right? I mean, of course, if something is far away, you see it at a lower intensity. But with light, what happens is light has all sorts of effects, right? For instance, it can go through a refracting medium, it can change its velocity, it can get scattered off, it can reflect, and so on, right? Gravitational waves, on the other hand, also these things also happen to gravitational waves, but they don't happen too much in the sense. So in the path of light, if you put like an opaque medium, it'll just stop. It won't reach you at all, right? But gravitational waves, uh, to stop gravitational waves, you first of all cannot stop gravitational waves completely. Even if you wanted to, you'll have to put a very massive object there. So because uh, gravitational waves do not interact with anything other than mass, and even with mass, it interacts very weakly. So basically, it's a very good approximation. To a very good approximation, you can assume that all the gravitational waves that left the system along your line of sight are reaching you just at a diminished luminosity, right? So that's the case for gravitational waves. Whereas for light, that is not the case. If there is some highly absorbing medium along the line of sight, all the light will get absorbed and none of the light will reach you. The probability of that happening is very low again. And especially in the case of 17 we saw that the merger of the two binaries and the light signal was probably offset by around a couple of seconds, right? And that couple of seconds is over 120 million years of its travel, right? Which is, I mean, 2 seconds compared to 120 million years is a very small number. So what we can deduce from that is light and gravitational waves roughly travel at the same speed. Yeah.
Okay, so I think Shikhar, you had a follow-up, right?
Oh yeah, I did actually have a question. So, one thing I really want to know is what were those final engineering accomplishments, between the 2015-16 period? You know what they were that just suddenly led to us discovering gravitational waves after so many years?
I mean, so first of all, I'm not an engineering person. I don't build detectors.
Yeah,
I would like to someday, but that day is not today for sure. But the main thing there is that there were a lot of incremental updates over the years. One, from what I understand, the biggest upgrades that went into you know a observing run of the detector, which I think was in the late 2000s, and the observing run which finally detected the event, was that they implemented a lot of um, technologies which relied on quantum mechanics. Yeah, so when you want to measure things as small as, 10 to the
yeah,
minus something meters, you also have to take principles of quantum mechanics into account. And a lot of the progress over the years was just that, you know, people, you know, people became more and more aware as to how to engineer quantum systems that can help us measure things perfectly. So I think those were the major engineering challenges that were accomplished over the years, which actually led to very good sensitivities of the detectors by the time 2015 happened, and then hence also led to the detection of the first event and almost 100 events since.
yeah, that makes a lot of sense. But before others continue to his questions, I also had one more. We often talk about dark matter, dark energy. It
Mhm,
essentially composes theoretically most of our universe, right? And
mhm,
it holds a lot of our galaxies, etc., together.
mhm,
That's just some theories. I don't think everything is proven just yet, right? Um,
mhm.
where where did they stand in terms of gravitational waves? What do you think gravitational waves could tell us about what makes up the majority of our universe in the future?
Yeah, that's an interesting question. So I mean, so to first things first, gravitational waves are coming to us from very far away in the universe, right? And so that means if they're coming to us from far away in the universe, they also tell us something about how the universe works, right? Um,
Yeah,
I mean, imagine it as like, you go to space and you sort of try to map the Earth and you see, I don't know, some patterns of light somewhere, some not. it tells us something about, like, where the light is coming from, and so on, right?
Mm,
Um,
mm,
but so anyway, my point is that, gravitational waves can tell us about, so for instance, there are ways to measure how much exactly is the proportion of dark energy, dark matter to the total energy budget of the universe with gravitational waves. There, I mean, one really interesting way is to try to measure how fast the universe is expanding with gravitational waves, the so-called Hubble constant. Um, and the thing about the Hubble constant, so the Hubble constant basically says, if I have it basically tells you how fast the universe is expanding. That's it. Now,
yeah.
depending, there is basically two different measurement ways in which Hubble constant is measured. So, for instance, one comes from the really early universe, and some comes from, let's say, the nearby universe. And both of them give different results. This is the so-called Hubble tension, Hubble constant tension, whatever you want to call it. And this they give us very different results, and nobody knows why. There are no, like, widely accepted explanations to it. So one of the ways in which gravitational waves can help is try to do an independent measurement of this Hubble constant, and uh, try to break this Hubble tension, and try to see where exactly the problem lies. Does the problem lie in the way that these data sets are analyzed, or is it something else, and so on? So that's one
Mm,
way in which um, you know things can, like, gravitational waves can tell us more about cosmology, this whole branch of trying to understand the universe. The other way is, like light, gravitational waves are also gravitationally lensed, in the sense it can bend around massive objects, and those also sort of tell us about the distribution of matter in the universe. Like,
yeah.
if we detect lensed gravitational waves, that could somehow it could maybe tell us about what kind of objects exist in the universe, what mass they have, and so on.
Yeah.
No, I think, and
Thank you.
I wanted to talk about this a bit later, but I think since you mentioned it, so
Mhm.
like I read one of your, like, at least one paper that you wrote talks about constraints on time variations of the gravitational constant using gravitational waves
Yeah,
in binary neutron
yeah,
stars. So
yeah,
essentially, a question that I had was, since you've talked about the kind of information that gravitational waves can tell us, and the basis of the paper
yeah.
is when a merger is happening, whether it's binary neutron stars or black holes, the gravitational waves have a particular imprint of that value of g, right? So beyond
Yeah.
this, like, if you could elaborate on the kind of information that gravitational waves carry, and like to what significance, or what entirely how significant is uh the information that they're carrying, whether it's relevant to the paper or just in general as well.
Yeah, so I don't exactly know what you mean by information, but basically, from the shape of the signal, it's you can basically get to know the mass of the events that produce the signal, how far it was, what else can you know? Where in the sky it was, how fast they were spinning, and so on, right? So that is the information that you can get from a gravitational wave signal. These involve using the data and sort of trying to compare it with different predictions from general relativity as to how the signal shapes would look like for a certain set of parameters. And then you use these basic set of parameters to make all your other astrophysical inferences, right? So, for instance, this problem of how fast is the universe expanding, you can the first step to do the analysis is to actually find out the source parameters from the data, like these masses, spins, how far it is, and so on. For the gravitational variation of the gravitational constant itself, what we used is, so, okay, why are we even interested in the variation of the gravitational constant? As we were taught in school, the gravitational constant is a constant. It's not
Yeah.
something that varies, right? But within general relativity, within Einstein's framework, it actually does not vary across the universe. So the variation is zero. Like, there's no all at all times in the universe, whether in the past or the future, it's going to be G equal to G, which was given by Newton, actually, right? Now, but what happens is that we know fundamentally that the Einstein's theory of gravity is incomplete, in the sense that it does not it breaks down in certain regimes. And when you try to come up with ways of trying to explain or trying to take away that breakdown of the theory, you end up with these so-called modified theories of gravity. And in some modified theories of gravity, the Newton's gravitational constant can vary. So it can have different values at different instances of time. So then it becomes important is that if you want to say that whether those theories are sane or not, if they are actually a real description of the universe or just some mumbo jumbo which nobody cares about, you have to actually constrain, say, something like the time variation of the gravitational constant. What we found in our work is that, at least as so far as we can see, there is no time variation of the gravitational constant up to a certain level present in the data, and everything is consistent with no time variation of the constant. So that's what we found in our paper.
Okay.
See, and see, sorry, do you want to go ahead?
No, Shikhar, you can go ahead.
Yeah, no, okay. So you were mentioning about the modified gravitational theories, and a lot of parts where Einstein's theories are breaking down, right? Do you think first you could elaborate a bit more on what you meant to talk about when you were saying that Einstein's theory breaks down at a lot of points? Sorry, at a few
Yeah.
points. And okay, no, I'll ask the rest after that. You can just if you can just
Okay,
explain this.
so I think the most famous of them is the fact that it is a black hole, right? So outside the black hole, we know perfectly well what happens. Even uh, inside the black hole, up to a certain distance away from the center of the black hole, we know what happens roughly. Uh, but we don't know what exactly happens in a black hole center. That's because if you try to solve Einstein's equation, you get infinities. And nobody knows what to make of these infinities. I mean, how do you interpret a number which is called infinity, right? Like, how do you physically
Mm-hmm.
interpret it? It's not a
Yeah.
physically realizable quantity. And this was pointed out by Einstein himself, right? I mean, it was not something that's something we know in retrospect. It was pointed out by himself. So, that's probably one of the wins of Einstein's theory is that, or the really great things about Einstein's theory is that even though it's such a successful theory, we don't know of any deviation from Einstein's theory at all so far, but it predicts itself that it is an incomplete theory. So especially when you go to extremely dense high densities and also extremely small length scales, that's when Einstein's theory breaks down. Because and if you have read about other kinds of physics, extremely small distances are governed by the laws of quantum mechanics. But quantum mechanics, of course, cannot describe gravitating objects. It cannot describe objects with mass. So yeah, I mean, and so the ideal theory would be where you try to sort of find a bridge between these two theories. And that bridge is, we don't know what that bridge is, but there have been some attempts in the past which naturally come up with some theories which sort of try to make that bridge. Even those theories that come up with the bridge are not complete in themselves. They have a lot of problems. But there are some which are more well motivated than the others.
Like the string theory?
Yeah, so string theory is one of those theories. String theory tries to put both of these together and sort of tries to come up with some theory. Like, so it's like saying that I come up with a theory which describes the situation which I mentioned, let's say the center of the black hole or whatever. But then at points, say outside the object, right? It should still follow general relativity because we know it describes the region outside the black hole very well. So yeah, I mean, it should have these nice special properties that it should have the correct. If you go to regimes where the theory is well understood, it should actually boil down to that theory and not give you some hocus pocus answer. So yeah, I mean, so string theory is one of them. There are other proposals as well. None of them
And what do you
are
think?
experimentally verified yet, for sure.
Yeah, absolutely. But where do you think gravitational waves comes into the picture of us as like the human race just trying to find a unified field theory?
I think gravitational waves are probably one of the best ways that, if there is this unified theory of unified field theory, gravitational waves are probably one of the only ways to actually test it, if it's true or not. Because, the scales that we deal with, I mean, these are the most extreme events in the universe. It can't get more extreme than this. So, that's why when you observe signals from two black holes colliding, that's probably the most extreme event that has happened anywhere in the universe, right? And then if not gravitational waves, then I can think of very few observational channels which can test things like string theory or something else. Having said that, I personally don't think gravitational waves are useful only for testing unified theories of gravity or whatever. And there are many other things which gravitational waves can test, especially about like how even if you say, sure, you might not have understanding of a unified field theory, but you don't have understanding of a lot of other things in the universe, like for instance how the universe grew and evolved as we know today, what kind of objects are present in the universe, what can you tell about the census of those objects. I mean, where do they lie, when do they happen, and so on. So gravitational waves are of course poised to ask or answer many more questions apart from just like, is string theory correct or anything like that.
I see. Yeah, absolutely. Makes sense.
Yeah, I think
It's its own independent field.
Yeah.
so. I think since we were just talking or touching upon like breaking down Einstein's theories as well, something that I wanted to ask you was the pair instability mass gap for black holes, especially
Mhm.
like their relation to gravitational waves. Because from what I've read, I think
Mhm.
in around 2018, we the gravitational waves were discovered, which were for a 65 solar mass black hole as well as a 85 solar mass black hole, right? And that they fall directly
Yeah.
between that region of black holes, which are
Yeah.
not you would not expect to exist, right? So do you like
Mm.
do you have any like theories as to how they came to be? Like I've read about theories that the 85 solar mass was itself a result of a merger of a black hole from before. Um,
Yeah. Yeah. So, okay. I mean, just to explain what the pair instability supernova gap is. So basically, what happens is, how are these black holes formed? These black holes form when really massive stars run out of their fuel and go supernova, and there's some remnant sitting at the end of it, which is a uh, what do you say, a black hole, right? But then there are so what happens is, like, when you add more and more mass onto a star, at some point, the star will not leave behind a remnant. It will just disrupt all on its own. And there'll be no remnant left behind. Basically, there'll be no black hole left behind. So people who worked in the evolution of massive stars basically said that, there will be a mass of a black hole beyond which there will be no black holes produced in the universe, at least by stellar collapse and so on, right? And this gap is supposed to be somewhere around 45, 50, 60 solar mass. Nobody really knows where, but people do think there are well-motivated reasons as to why the gap should actually exist. Okay, so that's about the PISM gap. By gap, I mean that there are no black holes above a certain mass. Okay. Okay, so that's one thing. Now, the merger that you were talking about is the so-called GW 190521. It happened in 2019, May of 2019, which we observed that it had a 65 solar mass black hole and an 85 solar mass black hole in it, which means they actually violate that upper limit on the mass. Now, uh, there's a lot of discussion on this event, and rightly so, because if it was actually 65 and 85 solar masses, that would mean a breaking of one of our standard models in the ways we explain massive evolution of massive stars. But it's not, at least to me, it's not clear that uh, you know the event itself had a very short duration and band in the gravitational wave data, which means that the source parameters that we actually extract out of it are prone to all sorts of problems, right? It's like saying that if I give you 2 points, I can fit a line to it, I can fit like some weird curve to it, and so on, right? So we are sort of in that regime with this event. And so any results, any claims that you see that, we have confidently said that this is a merger of I don't know what, should be taken with a grain of salt. And in May we restart our detectors. If there are indeed many more such events, we will see them in our detectors, and then we'll be able to say if the earlier events were real or not, and so on, right? So I think, especially with respect to 1905-21, this PISN mass gap event, my personal take is that we should just wait for like a couple more years, and then we'll be better placed to answer the question. I think that's my opinion on 1905-21.
Well, that's
We just
interesting.
haven't reached that level of certainty.
Sorry, can you say that again?
Oh, no, I was just commenting. We haven't reached that level of certainty yet. Well,
Yeah,
we
I
can
mean,
take
I
our
guess
time
the
and stuff.
the a more sharper point would be that like we can't be very certain just from a single event, which itself did not have a lot of information.
Okay, fair enough. Yeah.
Yeah, I think no. So, one of the things that I actually read was that the LIGO team itself considered whether, since you said that it was not clearly established by what they observed, they tried to consider the possibility of cosmic strings that were creating those kinks, which are essentially, if to whoever's listening, it's the ultra dense filaments that are about the width of a single proton, and I think 1 kilometer of length of theirs is probably as massive as the Earth itself. So do you think that could have been a source of the gravitational waves being uh, of the
I would be inclined to believe, like, of all the things, I would be inclined to believe that that is a less likely source of any of these events. Sure, I mean, it goes back to my earlier point that given like very little data, I can fit whatever I want to it, right? But I think of all the possibilities, and there are many, cosmic strings is probably one of the less likely possibilities. But yeah, this was my opinion. I mean, I'm sure there are people who disagree with me.
No, is there a particular reason like you believe cosmic strings are probably ruled out?
I mean, because first of all, cosmic strings, I don't know of a way to produce cosmic strings which is not like, I mean, sure, you can produce cosmic strings in string theory, but if string theory is not right, the base that you might have cosmic strings is not established yet. Whereas stuff like, there are other possibilities that 1905-21, which is that instead of it going around like this, it probably went around like this, like it was a head-on collision of two objects. That to me seems more likely because that's completely astrophysical, and we know that such mergers can happen. How often it can happen, how
Yeah.
likely it is, we don't know. And for that, we'll have to wait for like the next, I don't know, couple of years, 3 years maybe.
Yeah, that makes sense. So I think this second probably general research or general problem I want to talk about was the no-hair theorem. So it
Right.
I would correct me if I'm wrong, but I think it revolves around the fact that black holes don't have any extra hair or complicated details that other objects might have. So essentially, if you have two
Right.
black holes that have the same mass of the same electrical charge and angular momenta, but the first black hole was say made of collapsing ordinary matter, and the second was say made of antimatter, then it basically says that they would be completely indistinguishable, right?
Yes, that's right.
To an outside observer from beyond the event horizon.
Yes, that's right.
Yeah, so
Yes.
so essentially, I think the LIGO team played a role in uh, solidifying or verifying this theory itself.
So okay, I mean there are various ways in which you can think of it. So okay, like mathematically, the no-hair theorem is only strictly valid for a single black holes and not if two black holes are near each other. But that out of the way, uh, you know, the what one can do is, uh, when the final black hole is formed, it's you have two black holes which are coming and merging and forms one final black hole. But this black hole is a slightly deformed black hole. It's not a black hole which is stable. So it then now loses away all its deformities and becomes like one stable black hole. And in this process, it emits gravitational waves. And the gravitational waves that it emits should only be a function of its mass and its how fast it's rotating or its angular momentum. Charge is supposed to be very little for astrophysical black holes. So it's only a function of mass and spin, as we call it. And yes, we have basically seen these modes that when like these gravitational wave emission when these objects are trying to settle down into a final state. And those are very consistent with what we predict from general relativity. Um, whether to, I mean, there have been some claims in the literature that the no-hair theorem has been tested. Uh, it's a very strong statement to say that the no-hair theorem has been completely tested. But yes, what we can say is that the oscillations of these black holes after they merge follow general relativity. And in general relativity, if general relativity is true, no-hair theorem is also true. Yeah.
Oh, okay. So it's not like they've been definitely tested by any detection also.
Well, depends on who you ask, and what the exact question that you're asking. In general, to test the no-hair theorem, you have to sort of get many different modes of the final signal, and I don't think at current sensitivities we are able to current sensitivities, at least in the events that we've seen so far, we have not seen, let's say, we've only seen the dominant mode. We have not seen the other modes that should also play a part.
That's interesting. I think Shikhar, you had a follow-up.
Yeah, no, well, it's not exactly a follow-up. It's a slightly different question. It's to do with, well, the other day I was just reading a paper on Hawking radiation, so this just struck my mind here. Where do we link gravitational waves, your field of research, and
Hmm.
Hawking radiation in the bigger picture?
Yeah, I mean, so well, just for people who don't know, Hawking radiation is basically radiation that comes out of a black hole. So black holes, so that inspired this tagline called "Black holes aren't very black," in the sense that they actually give out radiation. Um, but this is, I mean, of course, Hawking radiation has never been detected in experiments, but
Yeah,
but as I understand, there are strong theoretical reasons to believe that it exists, right?
yeah,
Having said that, Hawking radiation will, so it you can think of it as extracting energy out of a black hole, and then at some point the
yeah,
black hole will just disappear because all the energy that has been extracted, and now the black hole will disappear. But the time uh, the time in which the time scale associated with this emission of radiation is larger and larger for larger black holes. So something like the black holes that we see in LIGO, Virgo, in the gravitational wave detectors that we have right now, they are not expected to have any effect from Hawking radiation. But there might be smaller black holes in the universe which might have effects from Hawking radiation. All is to say that the at least I am not aware of any direct ways to detect Hawking radiations using gravitational wave signals.
I see. And so we were talking about essentially smaller, more undetectable radiation from black holes here, right? I just wanted to
Mhm.
go off on a slight contrast and ask you about something. So something all of our viewers would probably know, most of them at least, is about
Mhm.
Sagittarius A, which is a
Mhm.
supermassive black hole theorized to be at the center of our Milky Way, right?
Yes, that's right.
And this is a very dense stellar environment,
Mhm.
and it's a region with a lot of neutron stars, possibly, right?
Yes,
And
possibly. Yeah.
yeah, and I had the view that there was research that showed, there wasn't convincing evidence of numerous such stars, but I
Mhm.
believe it's an open problem, and you have shown that you could detect the presence of these neutron stars at the centers of galaxies. Or
Uh,
could
yeah.
you
Mhm.
essentially explain where that problem's standing today, what you've done about it, and where we're going to?
Yeah. Yeah. So, I mean, first, I should say that what I have contributed is probably very small uh, portion of what is known about it. So, let's see. So, Sagittarius A star is this black hole at the center of our galaxy. So, at the center of Milky Way. Um, there is supposed to be a lot of star formation going on in that region, which also means that there's a lot of stars there. If there are a lot of stars, they will die and produce either black holes or neutron stars, and hence there could be a presence of neutron stars and black holes in that region, right? Now the point is, we don't know how many of them are there. That's an open problem, right? We don't know, like in what fraction are there. Are there more neutron stars? Are there more black holes? We don't know. We also don't know how they are distributed around the center. Like, where are they with respect to the black hole? How far are they, and so on, right? But one could definitely think that, if there are stars and then stars die and produce neutron stars, then it's also probable for these neutron stars to meet one another and merge at some point, right?
Yeah.
Nobody has seen such a merger yet, of course. But there are models that people come up with in which binary neutron stars can actually merge in these um, environments of near supermassive black holes. What I showed in my research is that if you have, how probable is it to actually um, um, actually detect, signatures from such objects, signatures of the fact that they are near the galactic center, near the supermassive black hole. How probable is it, and what physics we can get to learn about that? So one of the particular thing that I tackled was the fact that when two neutron stars merge, they have a particular signal which we actually don't know what it really looks like, because we are not so neutron stars merge at very high frequencies, and our detector is not sensitive to gravitational waves of that frequency. But if you have these binary neutron stars near a supermassive black hole, the supermassive black hole, what it'll do is it'll redshift. So do you understand redshift? Like sound is redshifted and blue shifted when you have like this Doppler shifted, like Doppler, you have a Doppler shift. So in the same way, the Doppler shift also works on gravitational waves. And the Doppler shift of the supermassive black hole, of the gravity of the supermassive black hole, could actually shift the higher frequencies into lower frequencies. But now we can actually detect these lower frequencies, and hence we can detect the presence of such objects near supermassive black holes. So that is one, sort of crazy idea that we put out on arXiv, put out into the world. If it's possible, it will be great if it is detected. But then we also mention in that paper that, there are, what the chances are, and that it's maybe we could see something in the next 10 years, or maybe not. Even if we don't see something, we can still learn a lot about if mergers happen around neutron stars or not, about around supermassive black holes or not.
Okay, thank you so much for that.
Wait, so
I guess Aadarsh should continue.
Yeah, no, so I think I just wanted to touch on something you just said. So essentially, we're not able to detect, we don't have high frequency detectors that can detect gravitational waves from a higher distance. That's why you're trying to enable it through, like you use a black hole to shift the light so that the frequency is low for us to detect.
Basically. Yes, basically that. So we can't. So in general, high frequency gravitational wave detection is very difficult, because then you are actually limited by, noise coming from the fact that photons are quantum objects. I won't delve too much into it, but suffice to say that, it's very difficult to detect high frequency gravitational waves. But the problem is that these the post-merger signal of neutron stars, the gravitational wave signal that comes out after neutron stars merge, is actually very high frequency. And hence, the only way we can detect them is if there's something which is pulling them to low frequencies. Right.
Yeah.
Oh, so like this was a paper that it was successfully proven, or is that something that's still out?
Well, it was an idea that we put out, like this could happen. It's still not seen yet, of course, and it will probably require some years to see it at least.
That's interesting. I think probably the last sort of idea that we wanted to touch on was I believe you published a paper about a couple of weeks back that was on impact of updated multipole love numbers and F-love universal relations in the context of binary neutron stars.
Yeah.
So Well,
Yeah.
just generally, if you could just tell us about the paper itself and sort of the key findings that you.
Right. Yeah. Hmm. So this is slightly tricky to explain. So what happens is that in when two neutron stars are very close to each other, they actually get deformed, right?
Yeah.
So they were perfect spheres earlier, and then when they come close to each other, due to just like the way that the Earth gets deformed due to tides of the moon, the same way this neutron stars will get deformed due to tides of each other. So there are these tides that deform each other. So that's one effect that is actually we have to account for while trying to um, analyze neutron star events, right? But we showed that there are other effects also that we need to consider, such as sure, this is one type of deformation, the fact that these neutron stars are getting deformed, but then there could be these neutron stars can also oscillate, like a single neutron star can also oscillate. And then when that oscillation frequency is the same as, let's say, the orbital frequency, how fast it's going around each other, uh, you can have something called a resonance. Are you guys taught about resonance in school?
Yeah.
Uh,
Yeah.
so yeah,
It's good in school. Yeah.
yeah. So you can have something called resonance, and that resonance. So basically, resonance is two frequencies, two separate frequencies matching with each other. And then when that resonance happens, there's an effect on the gravitational wave signal, which you need to account for. And that paper actually tried to carefully account for uh, these effects.
That's interesting.
All right. It is. Yeah, I really enjoyed that, and thank you so much for that. And before we close, I had one more personal question to ask.
Mhm.
Something I noticed, others noticed, and we mentioned at the start of the episode while introducing you, is that
Mhm.
you're interested in film, right? The art, you blog.
Yeah.
And so I'm someone who plays 2 to 3 instruments, and I write a blog, etc. How did you find a way to balance your research in physics with your time that you spend on your podcast and your blog, etc.?
Yeah, so I don't blog much anymore. I used to at some
Sorry.
point. Even the podcast, it's been defunct for at least a year, I think. Uh, but yeah, I mean, so the podcast was just something that we started, like me and one of my friends. We started during the pandemic, just because we wanted to have a bahana to meet each other every week and sort of discuss what we've always discussed, right? So we were friends in college and we've always discussed films. And we thought we were good at it. I mean, I don't know, like maybe people who listen to us should tell us if we're good at it or not. But yeah, that's how the podcasting happened. And it was more of like, just like everybody was in the pandemic. It was a lot of stress. I thought we could just relieve that stress by going and meeting each other every week. The thing that I've pursued the most seriously is theater. And that's basically what's been a part of my life since I ever came to Bangalore. And that I think, especially when we used to do in-person theater, in the sense like, not online theater, which also we have done, but in-person theater, it used to be a nice, I used to go to my institute in the morning at 9 o'clock and come back home at around 7:30 or 8 o'clock. And I used to eat food and I used to be extremely tired, like very, very tired. And then I used to go to my theater rehearsals. And by when I used to come out, I used to be such an energized person that I didn't even know what had happened to me 2 or 2.5 hours before. And I realized that it also helped me, first of all, stay happy. PhDs are stressful generally. So it helped me stay happy. Also, it helped me take my mind off my day-to-day work and get my time into something else. And above all, I really love the creative process and the sort of freedom and the rush that it gives me. And that's why I did theater all this time. Regarding how I managed that with my PhD, I mean, I think it's just like, I don't think there is any mantra to it. I just sort of went with it, and I tried to prioritize what I liked. And out of those priority sets emerged these natural sort of divisions as to the fact that I will work from this time to this time and then do theater this time to this time and so on. Same with films, right? I mean, I watch, I at least used to, in the last few months, it's been a bit less, but I used to watch a lot of films, like, at least a couple of films a week for sure. And then, so yeah, that was also like something that gave me happiness. I didn't do it out of like peer pressure or anything like that. It just gave me happiness and hence I did.
Yeah.
Yeah.
No,
Fine.
I think
Yeah, that's great to hear.
yeah, I think on this topic of creativity and expression, I think the last thing that we probably want to ask is a bit
Mhm.
untraditional way of ending things, but I would say, suppose you woke up tomorrow and there were no any monetary concerns or anything to do with experiments that you're running in gravitational wave astronomy. Just
Mm.
disappeared. Like the only problem that you had itself was uh, figuring or discovering things, right? And you were in charge of the
Mhm.
experiment or you were in charge of operations. How would you,
Mhm.
at least, how do you see, what path would you take essentially? And like, sort of, what would be the end goal or the big problem that you would want to solve? Someone who's not bound by like
Oh,
other considerations,
yeah.
whether monetary or ethical, things like that.
Hmm. That's a very interesting question. I mean, if I was not bound by anything, I would probably not do science, I guess. Like, I mean, I do science because I like it. And I think I'm good at it. But like, if given a chance and I could be whatever I wanted, I would probably be a movie star, I think. I would go work in the movies if that was possible. I don't think that's ever going to happen, sadly, and I'm stuck in
Would be
science. But
fun.
I'm not complaining. But I would love to be a movie star. I would. I mean, I think I'm really in love with like certain kind of movies, and I would love to be that. But if you're asking me specifically in the context of science, were you? Sorry, I didn't.
Open-ended. If you like,
Okay,
you
I
woke up
see.
tomorrow,
Yeah,
yeah, just anything. Like,
yeah.
no
So in
science.
the context of science, I think I would then leave. I mean, of course, I don't do experiments. I do my research is more theory and computation, but I use data. So I would in research, if you gave me a choice and said that I have infinite money and you can do whatever you want, I would probably go and learn how to build a gravitational wave detector and you know focus my efforts on how I can build more of them around the world. I think that's what I would do. But yeah, this is within science. I mean, I actually would like to be a movie star.
So movie stars probably the better one.
Yeah, yeah.
Yeah, I think that
I'd say this happens a lot in India.
What happens a lot, like movie star, like wanting
No,
to like doing
yeah,
something
we
and
have
then
those
wanting to do
dreams.
something else.
Yeah,
Okay.
we have these dreams of becoming movie stars, musicians,
Yeah,
maybe artists, and then in
yeah,
the long run, we all become engineers, doctors, or lawyers.
yeah. I mean, I would like to think that I mean, so I have an engineering degree. I'm glad that I didn't pursue engineering because I would have made a very bad engineer. Um, but yeah, I mean, if like somebody was giving me a break in the movies, I would leave everything for it. I think.
Yeah,
Yeah,
for sure.
yeah.
I think that's
Right.
nice way to end things. But thank you so much for joining us today. It's been
Thank you
quite
so much. I'm
learning.
really glad that I came on the podcast. I got to talk about a lot of things. I've generally felt this in the past that when one there's all these thoughts that one has, and then but when somebody's actually trying to have a conversation with you, and those thoughts come out as words, that's when like it gets also solidified in your head. So I could
Yeah,
solidify a lot of thoughts in my own head. So thank you for that.
No, thank you. It was
yeah,
lovely.
we really appreciate you coming on here.
Yeah, I think
Yeah,
Thank you.
me and Shekhar definitely learned a lot. I'm sure everyone who watches will definitely learn a lot.
for sure.
Maybe they're too inspired to become movie stars someday.
Yeah.